Okay, so here we're talking about the vector equation of a line. So looks very different from the good old normal thing that we've seen with lines in 2D where we have y equals mx plus c. We all understand that one. M is the gradient, y is c is the y-intercept. This looks really different, this thing here. So we really need to make sure that we understand each part of this equation here. So the r part on the left-hand side, you could think of that as any point on the line, x, y, and z. Okay, written in component form, a lot easier. A is a vector. Let's just do an example here. That's any point on the line. And this example, they've got t, I'll use lambda. That is a scalar, a number, and then b. Okay, b is the vector in the direction of the line. Okay, so any point on the line here. This is giving us a general point. The second one here, a is just any point on the line, could be anything. Lambda is a scalar, just a number. And this vector here is the direction that the line is going in. Okay, so for 2D lines, I mean, we've only got three things that could possibly happen. They're either intersect, they're either parallel, or they're the exact same line. With 3D lines, it's a little bit trickier. If we have lines in 3 dimensions, they can intersect, of course. They could be parallel, they could be the same line, or this one here, they could be what we call skew, which means that they don't intersect and they're not parallel. Okay, we can still work out the angle between them by thinking of the projection of the line on the other one, but they're called skew lines. So a little bit trickier. Let's check this one out. Are these two lines parallel or not, and give a reason? Well, the thing we're looking for here is the direction vectors of the lines. When it's written like this, it makes it a little bit tricky to see, but you can see it. For this line here, that's the direction vector, and I mean, you might even want to write that out, -1, 3, 2 in component form. Here's the direction vector for the second line, which is 4, -12, -8. Now have a look at those. Are they multiples of each other? Yeah, they are. The second one is -4 times the first one. In other words, these lines are going in the same direction. It's just that this first line, if we compare the direction vectors, this direction vector here is 4 times the length and going in the opposite direction, but that doesn't matter. It's still going to be the same direction. Okay, so those two lines are parallel. The only other thing now is to think, well, are they the same line? And check that out. Well, we can check that out by looking at the points that are lying on the line. And in both of these cases here, no. We've got 2, -5, -6, 3, -6, -6. So these are different lines and they're not intersecting with each other. Okay, this is the last example in this video. I'm going to be looking at a bit of a tricky question here. We're going to talk about how to find the closest distance from a line to a point. So we've got a point Q here, we've got a line travelling along here. We want to know really what's the point on that line that's closest to Q, and then how far, what is the distance from that point to the line. So check this one out. This is a bit of a tricky one. So again, I'm not going to be able to draw this. There's no way, but I can just, draw some random line, some random point, just to give me an idea. It kind of helps just to get it in my head. Okay, so there we go. Here's the point here that we're looking at, and that's going to be point Q right there. Okay, I'm going to call this point here on the line M. It doesn't matter, I'm just giving it any kind of label. And here's our line going along here. Okay, so notice that the shortest distance from a point to the line is going to be when we get a right angle, correct? Yeah, absolutely. Yeah, of course that is true. All right, so let's do this one here. So if I just zoom in here for a bit, so that angle there is going to be 90 degrees. Okay, simple. Okay, let's do some work this thing out. All right, so How do we work out between vectors whether two vectors are perpendicular? Well, it's the dot product. So we're going to want to do the dot product between the vector from Q to M, the dot product of that with the vector in the direction of the line, which I'll call B, and we want that to be equal to 0, correct? Yes. Okay, because we know that when the dot product's 0, we know the two vectors are perpendicular. Okay, cool. So we've got the vector in the direction of the line. I can write that one right down now. That's 2, 1, minus 1. That's this thing here. That's the vector going in the direction of the line. Okay, now we need the vector in the direction from Q to M. Now Q is the point 1, 2, 2. What's the coordinates of M? Well, M is any general point on this line. So just let me rub this out here. So what is any general point on this line? Okay, that would be, for the x coordinates, -1 plus 2s for the x coordinates. Remember, s is a scalar. 0 plus s for the y coordinates, and 2 minus s for the z coordinates. Okay, so if I just plug in different values of s, that's going to give me different points on the line. So that's the coordinates of M. M is any general point on the line. So if I want to go from Q to M, we remember the little formula, that's just M minus Q, where M and Q are the position vectors of the point M and the point Q. So the position vector, let me zoom in a bit here. So we've got -1 plus 2s. The s for the y coordinate, and 2 minus s. And we know what Q is. Q is 1, 2, 2. That's the position vector of the point Q. So what does that give us? -1 take away, so it's -2 plus 2s, s minus 2, and 2 minus s minus 2 is just minus s, or -s. There we go. That's the vector Q to M. Cool. So I'm going to put that right up here in my dot product. -2 plus 2s, s minus 2, and -s. Awesome. So the dot product there has got to be equal to 0. So let's do the maths. Easy. So from that, I'll switch to red. We've got -4 plus 4s, the top one. So I'm just multiplying these two together. 1 times s minus 2, which is just s minus 2. -1 times -s, which is just s. That's equal to 0. So let's tidy this up. Obviously, we're going to solve for s now. 4s plus s plus s. So we've got 6s. -4, -2 is -6 equals 0. S is equal to 1. Wasn't that nice? Yeah, so s is equal to 1. So what's the point? What's M? Okay, let's go up here. So what is M? Well, we said that M is any point on the line. So if you look at this, that's any point on the line there. So we just have to replace S with 1 in this case here, and we'll get the coordinates of M. So if we replace S with 1, what do we get? We get -1 plus 2, which is 1. 1, 2 minus 1 is 1. Wow. -1 plus 2, yeah, that's correct. 1, 1, 1. So that's what M is. M is the point 1, 1, 1. That's the closest point here. Easy. And the last bit, which I reckon you'll be able to handle, is just what is the distance? And that's just Pythagoras' theorem. So if I want to know what the distance from Q to M is, distance, it's just going to look like this. It's going to look a bit strange, but so going from the point Q to the point M, so 1 minus 1 squared plus 2 minus 1 squared plus 2 minus 1 squared, the square root of all of that. So that's the square root of 0, 1 and 1, root 2. There we go. Done. I know that was a long example, but that is how you find the shortest distance from a point to a line.